The supermarket aisles are a graveyard of industrial waste, designed to keep you dependent on a fragile supply chain that could snap at any moment. They want you to believe that growing food requires hectares of land and expensive chemical inputs, but they are lying to you to maintain their monopoly on your survival. We are going to reclaim our sovereignty by mastering the fluid dynamics of life itself, utilizing ancestral engineering adapted for the modern disruptor. See how you can build a $150 NFT hydroponic rig to establish a continuous harvest cycle for your household, starting now. Biological autonomy requires replacing fragile industrial supply chains with localized, highly efficient biomachines. Every system engineer faces a primary architectural choice before laying a single pipe: building an open or a closed system. Open systems function as conductive drains. You pump a nutrient solution over the roots once and then discard the excess directly into the environment. It requires high continuous inputs and guarantees a heavy waste output. This diagram demonstrates the mechanics of a closed-loop system. Fluid pulses from a central hub, flows through the structural veins to hydrate the plants, and returns to the reservoir with zero fluid escape. Recycling the nutrient solution minimizes the raw materials you need to import. Operating a closed loop introduces a strict engineering constraint. Because there is no earth or soil to naturally buffer the pH and mineral levels, the operator must actively steward the precise chemistry of the water. A closed loop minimizes waste and leaves a negligible footprint, providing a level of resource efficiency that is critical for long-term off-grid survival. Plants present a strict biological paradox. The root zone requires continuous hydration to survive, but total submersion in liquid strips the roots of access to atmospheric oxygen. Beginners building static systems trap roots in still water. The dense fluid physically blocks oxygen from reaching them, suffocating the organism. In an engineered off-grid environment, water must perform two simultaneous tasks. It has to act as a nutrient carrier and an oxygen conduit. Static fluid introduces a secondary risk. Without kinetic movement, minerals separate and fall out of solution, while pathogens rapidly multiply in the stagnant zones. Static immersion guarantees biological asphyxiation. To keep the system viable, the engineer must find a dynamic kinetic solution to maintain flow. The kinetic solution to the stagnation paradox is the nutrient film technique, or NFT. An NFT system requires a 1:30 downward tilt in the channel for continuous fluid momentum. By restricting flow to a thin film, only the root tips touch the liquid. The remaining root structure is exposed to air, completely preventing asphyxiation. The design does carry a strict point of failure. If kinetic flow stops because of a pump failure, the minimal liquid in the channel drains instantly, and the exposed roots will desiccate rapidly. By decoupling hydration from total submersion, the NFT protocol delivers nutrients continuously without sacrificing biological oxygenation. Decentralized fabricators can push fluid manipulation even further by transitioning from liquid films to atmospheric mist. This is aeroponics. Aeroponics substitutes the flowing liquid channel for a high-pressure atmospheric mist, suspending the entire root mass in a 100% oxygenated void. Achieving this requires advanced hardware physics. High-pressure pumps force liquid through specialized nozzles, violently shearing the dense fluid into a swirling vapor. This dimensional breakdown chart compares a standard fluid drop against an atomized cluster. For optimal biological absorption, the nozzle must shear the fluid into droplet sizes between 20 to 50 microns, multiplying the surface area exponentially. Aeroponics demands a significantly higher energy draw and complexity budget, but it yields the highest biomass output per square inch achievable in a controlled environment. We translate these fluid dynamic theories into a practical bill of materials for under $150. The core architectural foundation requires a central hub. A standard 20-gallon opaque tote serves as the biological reservoir for the closed system. This exploded blueprint details the assembly. 4-foot PVC pipes drilled for net pots route via flexible tubing to the 20-gallon base. A submersible pump pushes fluid vertically, and the 130 tilt utilizes gravity for the return trip, conserving electricity. Applying rigorous fluid dynamics transforms cheap, locally sourced hardware into a self-sustaining, high-output biological machine. The system is modular. You can calculate the pump's exact pressure and volume limits and add extra PVC channel lengths to the baseline reservoir until you max out the kinetic flow. The ultimate efficiency metric of this closed-loop architecture is water conservation. It operates on 90% less water than traditional open-soil gardening. You have the blueprints. The industrial food system is one option among many. By mastering the nutrient film technique and the principles of closed-loop engineering, you've taken the first step toward true autonomy. Join us at Unearth the History as we continue to dig up the forgotten methods of our ancestors and adapt them for our survival. Reclaim your yard, secure your nutrition, and break the chains of dependency. Subscribe to join the resistance and turn your backyard into a fortress of production. True sovereignty rests on engineering biological systems that bypass centralized control rather than simply hoarding resources.